Welcome back to CS 532W UBC. I'm still Frank, and we're still enjoying this course together. Okay, so as kind of a weird interim lecture, knowing that homework is due today, I thought that I would take you through sort of an old school, like what do you do when you're going to like build a sampler, think about like fancy sampling, like build a particular model, build a particular sampler for it, think about like things in an old school pre-Prob Prog kind of a way. And in particular, I'm going to talk about an HMM variant before probabilistic programming, and it will help maybe make up for the fact that I, more or less completely butchered when I was talking about HMMs before, because I knew that we were going to talk about them like 800 times through this course, and that's fine. So today, there's a couple of tricks in here. There's even a project idea that will show up we'll talk about. But today the goals are to sort of show how you think about inference and think about designing inference algorithms for particular models, particular advanced inference algorithms before probabilistic programming, or before just being able to write down something and apply a general purpose inference algorithm. I want to make you aware of some of the inference techniques from, in particular for hidden Markov models. We won't go into a huge amount of detail about them, but you should be aware that there's a webinar tutorial, but all the modern machine learning textbooks have excellent treatments of HMMs. HMMs are very, very central to all kinds of data analysis problems, but we've been talking about Markov models, and we're going to get to probabilistic programming in a little bit. But one perspective on probabilistic programming is kind of a crazy one to think about, but is a perfectly valid mental model of what a probabilistic program is. It is if you take the entire virtual memory state of a computer, and then when you have a stochastic transition, in other words, you make a random sample, you draw a random sample or something like that, that transitions the virtual memory state of a process from time step 1 to time step 2 to time step 3, so on and so forth. So you can think about a probabilistic program with sample statements as just being an HMM, but just is a little bit crazy because the latent state in the HMM is the entire virtual memory state of the process. Okay? So when we talk about HMMs, even if we might do, like later in the course, we'll talk about variational RNNs and these sorts of things, which are kind of modern generalizations of HMMs. They're still just HMMs, first of all. But second of all, we should be, thinking that this world model for RL, for language, for whatever, it's all sort of a special case of the big probabilistic programming case of the model of the world is literally just a simulator, your program evolving through time. Today, what we'll talk about is some work that I did a long time ago on what are called semi-Markov models. We talk about them as explicit duration HMMs. They're interesting models in their own right. You might have clinical applications you want to use them for, so on and so forth. But kind of the point of today's lecture is more to drive home the point that if you have some model, we're going to write down, I'm going to motivate why we want to have an explicit duration HMM. We're going to write down a graphical model for an explicit duration HMM, and then we're going to think about how to do inference in the thing. And you're going to see that there are some interesting issues that arise, and you have to deal with them. You have to come up with bespoke inference algorithms and so on. You have to derive a specific kind of inference algorithm, so on and so forth. Whereas if you stick it into a Prob Prog system, you would just get a general purpose inference algorithm. What might not work as well as the inference algorithm that I'm going to talk about today for this particular model, but you don't have to go through all the craziness in order to get there. What will come out also are some tips and tricks for Bayesian inference in general. In particular, there are a couple of techniques which, again, will point to project opportunities, so on and so forth, and just general tricks that you should be aware of in general when you're doing Bayesian inference. And those are the use of auxiliary variables. And we'll see a huge example of that when we do Hamiltonian Monte Carlo later. But here we're going to look at slice sampling, which is a particularly thought-provoking form of an auxiliary variable trick for inference. How many of you have heard of slice sampling? Awesome. Okay, great. This is like one of these little tricky things. So there is that come from this directly. You know, if somebody wants to work on a particular very like Prob Prog kind of thing, project ideas for dealing with discrete random variables in general probabilistic programs and general purpose inference, you might actually just steal some of the techniques that we talk about today directly. So hidden Markov models, historically, they've been around for a long time, are an important tool for data exploration and engineering applications. They are still used. In fact, the faculty candidate who was interviewing today was a natural language processing person, a speech person, and we were having an argument, which she won, about whether or not deep learning systems just like totally take over the world and should be used for everything. And then she basically said for low resource languages, indigenous languages, that sort of thing, where you don't have a lot of labeled training data and so on and so forth, traditional machine learning techniques that use, you know, HMMs as the backbones for automated speech recognition systems, so on and so forth, they still beat deep learning systems relatively handily in low resource domains, right? I see that Vasilios is arguing about that, but how many times have you worked on a low resource domain language?
I worked on a multilingual model before, which involved also low resource languages, basically.
Fair enough, but yeah, okay.
I mean, explicitly on low resource languages, yeah, I can see that. But if you take the advantages of a model trained on high resource language,
I completely agree, particularly if they happen to be in the same language family and these sorts of things. But in particular, this faculty candidate worked on, for instance, North American indigenous languages, right? In which there's like nothing, right? So that's the point. So I was actually arguing your point of view, and then she convinced me that in fact actually the old school stack still wins in those cases. So there were lots and lots of speech recognition, natural language processing applications. We'll talk about handwriting recognition applications just a little bit, gesture recognition, so on and so forth, financial data modeling. These things still are relevant. And in fact, actually, the reason why I chose to give this particular work to you is that this is effectively some sort of switching kind of HMM, which is something that you could use in another project idea where you make interpretable variational RNNs that have explicit interpretable state switching in them, and hopefully that will become relatively clear later. Okay. So we had the graphical model for a hidden Markov model before, and let me go through it again relatively quickly here. And just for the fun of it, also for all of you, I haven't given this talk for probably 15 years. So I have, you know, it's going to be fun for me as well. I've reviewed it, so it should be okay. But if, you know, I sometimes challenge myself with this as well, just to see whether I can remember my own work. It's kind of fun. Okay. Anyway, so hidden Markov model, what have we got? We have some observation space. The Ys are going to live in our observation space, and we have some, typically, but not always, depending on how you define what an HMM is. A statistician would define an HMM as just having a structure that's like this, a latent state that's unobserved, and an observable state that is conditionally independent from all other times given the latent state. But computer scientists typically refer to HMMs as models in which the latent state is discrete. So Z will live in some set, 1, 2, 3, 4, or something like that, integer valued set, or indexable set, integer indexable set. And Ys could be anything. They could be strokes, they could be Kepstro frequencies, a spectrum, spectrograms for a time slice of an audio signal, so on and so forth. And the point is, pi will be the set of state-dependent transition distributions. So you can think of, for instance, I ate my cat, or something like that, right? That's kind of gross, but you get the idea. So for every spoken letter, right? So Zs could live in the space of letters. So in English, we'd have our favorite 26 letters or whatever. And the Ys might be a spectral decomposition of audio signal and basically power at in different frequency bands, right? So there is some transition distribution from I to A and A to T and T to E and so on and so forth. And the probability of going from I to another I is pretty low. Probability of going from I to a consonant is pretty high, so on and so forth. So there's going to be a probability vector over the entire vocabulary, condition for each element, for every state, basically for every element in the vocabulary. So K would be the, equals 26 in this example. And then there would be some, now if we were going to marry deep learning and whatever, we would have some sort of, I guess what's the, I'll ask Vasilios what the most recent sort of like wave to letter. I think there is even a wave to letter that exists now. So in other words, you can get a pre-trained neural network that actually goes from some segment of speech signal and returns to you some embedding that is a representation of the speech signal in a period. It can even actually return to you a vector encoding the probability of a particular letter. Yeah.
Yes, I don't remember the name, to be honest, of the method, but it does exactly what you said.
Exactly. So the point is, you have some sort of audio signal. There's some big neural network, whatever, that it's a feature extractor, and it produces some observable, maybe the last layer of the neural network, something like that, for every time step. Okay, and there is a conditional distribution that you can learn through this HMM procedure or so on and so forth. It's basically the observation distribution and its parameter that, given a particular letter, there is an emission distribution over, for instance, this feature vector return from a deep neural network, which says how likely it is that a particular feature vector would be generated if I were to say the letter I, or a word with a letter I in it, and then ate my cat. Again, I don't know why I chose that. It means that I probably have some sort of sickness that needs to be addressed. But so great. So what we would be given is this sequence of, and these double circles sometimes stand for observations. That's fine. What would be given are the sequence of neurally extracted feature vectors. And in some cases, we would be given the thetas and the pi's. We might actually want to do inference over those. We might want to learn them. Today, we'll assume that we're given those. So somebody will have given us at least a training corpus of letters and corresponding vectors, so we could just estimate this conditional distribution directly. And we would be given a corpus of English text so that we could estimate all of these conditional distributions directly. So these are not unknown in this particular case, although they can be relatively straightforwardly. We'll just say that they're known. Does that make sense? Any questions about that? Everybody understand how you would get the value of pi, estimate the value of pi, and estimate the value of theta?
I have a question.
Great, awesome. Ask away.
It's a notation question primarily. It is the same question I asked last lecture. So is K related to T at all, or is because you say K is 26, so I'm assuming that's because there are 26 letters in the alphabet, and so that's like the number of random variables, and then that's
not the number of random variables, that's the space in which, so let's see, Z, T lives in some vocabulary. So you might as well get used to seeing sigma as a vocabulary. We'll say that sigma is is some integer indexable set.
Mm-hmm.
Okay, such that the cardinality, unfortunately I put 0 in here, so I'll put -1 here. The cardinality of that set is K. The number of random variables.
Oh, I see.
The number of random variables in this particular model is T plus 1, because we have a 0th state and then T. Okay, and all of the random variables are discrete quantities, which means that pi m is some discrete distribution, is a conditional probability density, which is index. So pi m equals p of z
Probability of the
plus
m
1, given that zt equals m.
Okay. Okay. Thank you.
Awesome. Thank you. It's totally awesome. And py t given zt is some distribution. We'll often in our stuff, I guess, use g. It will just be some distribution g parameterized by theta of zt. So in the particular case of, in this example application that I'm giving you of letters, right, you can go through a very long corpus and look at, you know, every instance in which you see an I, and you can just count up the number of times a letter occurs in the next time step, and that gives you the conditional distribution of the next letter. So you can estimate pi directly for all letters directly from a corpus. And we can go into language models and that sort of stuff. We can go way into that if you want to. But assume that we can estimate those just by counting and get a reasonable estimate. Or somebody hands us a good pi. And the same thing for theta, provided that we have labeled sequences. You know, here's a bunch of letters, and here are the feature vectors that a neural net has extracted from an audio signal. Then we can fit a density estimate. We can find some family for G that matches the distribution of in our vector space, whatever y happens to live in. So yt will live in some, you know, I don't know, r to the 50, some real valued vector space, right? And G will be a distribution over that space with a parameter that's unique to each state, each value a state can take. Okay, so then in this particular case, the inference problem is you're given pi's, you're given k pi's, you're given k thetas, you're given G, and you're given all of the y's. Okay, then the question is, what are the z's? Like, what was actually spoken? What sequences of letters, or what distribution over sequences of letters? What's the posterior distribution over sequences of letters given the observed, you know, audio feature vectors? Time sequence of audio feature vectors. Does that make sense? Okay. Just for the fun of it, while we're here, just to drive home this point, okay, we've got this on video, so I should be, that's not going to do it, is it? No, that's annoying. Just for the fun of it, let's just go through one more little example of this, just to give you a sense. Okay, that wasn't so bad. Let's go through another example. Okay, here, this is foreshadowing. I don't expect this to necessarily make sense. Now I'm going to have a very hard time saying what the space, I can't even really write down what the space of virtual memory, I mean, you know, what's the size of an address space in a modern computer?
Mia put in the chat. You were waiting to hear the answer.
Yeah, so that's the number of addresses, right? But then there's actually the number of bits, right? Which would then be whatever, like this, something monstrously huge, right? And in a probabilistic program, we know all of the transitions because a program tells you how to transition from here to here. right? So when you write a program, it tells you how to transition from one virtual memory state to the next. Okay? Some of those will be deterministic transitions, some of them will be stochastic transitions, right? And if you observe part of the virtual memory state to have taken some value, or your program is endowed with observations, then you will have some then y will live in whatever space you specify in your program or whatever. And the act of probabilistic programming inference is to, given a program which specifies this, and frankly actually also specifies what is observable and what is not, and what the distribution over those observable things is, and the values of the observable things, what is the sequence of virtual memory states that the program went through in order to explain the observations. Okay. Does that make sense? Probably not yet. It will over time if it didn't make sense just now. That's one of the things we'll get to. But I want you to stretch and think about the fact that like that's what's going on. Later on in the course, we'll refer to these transitions as F, and we'll refer to these transitions, these observation distributions as G, and they will be denoted with sample statements in the program or deterministic operations, which again we can get to via program transformation, and these will be observed statements. Okay, and this would be what we'll refer to as trace-based. So what we're looking at here is a trace of a higher order probabilistic program. Okay. When you start writing your evaluators in homework 2, which Berend will tell you all about, you will focus on this part. And then homework 3 will be this part in various flavors and forms. Cool. Awesome. Questions? Concerns? Comments? All right. Okay, so the notation we'll use today looks like this. So, and this explains this A matrix that I was trying to talk about before and did in an absolutely hideous way earlier. So, the conditional distribution of Zt, given that Zt minus 1 equals m, will just be discrete with some conditional probability. It's a conditional probability, and it's conditional on the parameters of a discrete distribution are given by pi m. That's a k long vector whose entries sum to 1, and then yt given zt equals m is distributed according to some likelihood that's application specific, whose parameter is given by a state-specific parameter. Okay. And you can collect up all of these conditional distributions into a matrix A, and you can sort of relate this to the Markov model thing that we were talking about before, because if you take A transpose and multiply it by some k-length state vector, you will have a stochastic transition to, it's basically it's exactly the Markov model that we were talking about last lecture, right? You have a system that transitions in a Markov way, and there's an equilibrium distribution, and so on and so forth. But again, what we're doing here is not, the Markov modeling that we were doing before, designing transition kernels and so on and so forth, but is instead to ask, given that we can observe some aspect of the state of the Markov model, but we can't actually see the full state of the system, what is the full state of the system over time? Okay. And one way to think about this, and this is Chris Bishop that did this, is you can sort of think about this, an HMM, if you have, for instance, Gaussian likelihoods, as a dynamic mixture model. So we've talked a little bit about mixture models where you have, some class assigned. You draw from this by drawing first a class 1, 2, or 3. If you draw class 1, and then you draw from a mixture distribution, you draw from class 2, then you draw from that density and draw, so on and so forth. The HMM basically says, I'm going to transition from one class to the next according to a conditional probability density, and then I'm going to draw from that class, and so on and so forth. So this might be in R50, the distribution of spectral audio feature vectors corresponding to I, and this might be the feature vectors corresponding to A, and these might be the corresponding feature vectors for T. And the black lines indicate like how you move between these bits of observational space, and the bits of observational space are the distributions over the observational space, whatever that happens to be. Clear enough?
I have another question.
Awesome, thank you. You know, every single course has to have at least one. It's better that there's more than one of you. We really need like 3 or 4 that just speak up and ask questions. So, you know, don't make Emma be the one to ask all the questions that everybody else actually has. Please, you know. But okay, yeah, sorry.
So what is a mixture model?
Okay, that'll come up. You'll get it in your homeworks. But a mixture model is basically when you write down some density. So this is p of x. Okay, but we say that this somehow is some weighted combination of, for instance, so we say a density, like we know our simple densities. We know normal, gamma, Poisson, beta. We may not know what they are, but we know of their existence, right? One of the things that we'll start thinking about quite a lot, particularly when you start thinking about posterior distributions, right away you'll recognize that the posterior distributions that we're talking about do not fall into one of these families. There's some other kind of thing. They're a distribution, but they unless you're in the fancy, you know, conjugate family form space, they're some much more complicated thing. They're multimodal and so on and so forth, right? But it may be that, you know, there are, you know, let's go with, you know, you want to do a density estimate for an insurance company of like human height and weight, and you plot out everybody and you find that there's like a non-Gaussian distribution of those things, but you still need a density estimate. So how do you write down a density estimate for it? One way to do it is to write down a mixture model like this, which just mixes underlying distributions like normals, and you have 3 of them, and they have particular weights associated to them, and the overall density is just a mixture. Right. So an HMM you can think of as being if you think of the time marginal, if you basically generate from an HMM and then forget time, just collapse the whole thing across time. I guess I should be moving my hand this way for time. Then what you have is a mixture model, because it will have sampled from mixture densities according to each state at each time step.
So just out of curiosity, like the picture that you have on the right, the ordering of the sequence is in a nice way such that you visit all the blue first, and then you visit all the red, and then you visit all the green, right?
It's highly unclear what's going on. It looks like in this particular HMM, there is a very large amount of self-transition, which is to say that the pi vectors have large probability of staying in the same state. But note that there is at least one transition back here somehow, right?
Do you have to fix the ordering of which points to visit? Or
No.
does it do by itself?
No, I mean, that's these transitions from, you know, what's missing here is that for all green points, you know, Z for all of these is equal to 2. Right, and for all of these points, which I don't know what time indexes there are, all of them have Z equal 3, right? So I don't know, like maybe, let's say this is Z1 and then Z2, and I have no idea what happens from this point forward, so on and so forth. But the transitions between the values of Z are governed by these guys.
Okay, yeah,
right?
That makes sense.
Great, awesome, sweet. I don't know if you're in a position, Amara, to turn on your camera, but it's the thing in this course, so we can see each other. part of getting to know you and achieving what's the credit for that? Participation credit. That's right. Yes. Although I'm sure Emma will figure out a way to get participation credit in some other way, and we'll twist my arm somehow. Late homeworks, participation credit in some other way. Anyway, who knows? Maybe somebody else will do it. Okay. You can also think about, in terms of, this is not a graphical model, and I thought about removing this slide. You can also think about, particularly when you talk about inference algorithms, quite often people historically have talked about trellises, and these are basically, an HMM takes a particular path. So you might start with Z equals, 1, and the edges here are the weights in the entries in this matrix A, and they correspond to the probability of transitioning, say, for instance, to Z2 equals 3, and Zn minus 2 equals 1, Zn minus 1 equals 3, Zn equals 2, so on and so forth. Okay, and all the weights on all of these edges are just the entries in the transition matrix, or one of the entries in the K vectors. Pi vectors. Okay. Okay. So another example is, if you have, if you're doing handwriting recognition, I ate my cat. God, whatever. I can't believe this is being recorded and put on the web. Anyway, so training data might be, an observed sequence where Y is the joint values of the vertical and horizontal position of a stylus at a particular time, right? So Y can be not just scalar, it can be a vector, as we just talked about, right? And you might train a bunch of different models one for each character, the latent. So in other words, you might have HMMs for every single letter in your alphabet, whatever that happens to be. The latent states can be designed to correspond to the strokes. And then you can use you can classify new stylus sequences using the trained models by basically computing their evidence under the model, right? So you can compute this evidence by integrating over the posterior, having some prior on which character you think occurs, and then basically do Bayesian model selection like we've talked about. Okay, this is an example application. So. In order to make things hairy enough to be interesting for us to talk about, so we're not going to do forward, backward. We're not going to do belief message passing or belief propagation or whatever, which is something that we could do. It would take a couple lectures to do. We're not going to do that because they're not actually general purpose and can't be used in every probabilistic programming setting. But we can talk about some other stuff that is more general. And to get there, we'll make the HMM a little bit more complicated. So in real life, in basically most applications, the latent state dwell times, like how long you stay in one state, and Jason already pointed out that there's in the figure we saw, things tended to bounce around in the same state, but in actual fact, there's some marginal distribution of so what's the probability that this latent state stays the same for L time steps? So basically it's saying Z t to t plus L equals M for any value of t, but the L is the important part here, given this matrix A, right? The stochastic transition matrix, right? Well, we know that the states, because of the graphical model, forget the observations for a second. We're just talking about the states. This is a description of the prior. All of the state transitions are independent or conditionally independent. So we can just write down the probability of that sequence as just a product over the L time steps of drawing the same state over and over and over again. And when you do that, right? That basically corresponds to a geometric distribution with parameter L. So that's the probability is equal to the probability of L successes and then one failure with probability pi m index m, stay in the same state, right? So that's the prior that HMMs impose on the latent state dwell duration. And that's often not in correspondence with reality. And there are often problem-specific structural constraints on allowable transitions. In other words, you might say that self-transition is impossible for whatever reason in whatever application, or transition to states before are impossible. So you might be an online retailer, and you might want to know whether or not somebody was married. You know, like there's a distribution over marriage. You know, single, married, and then previously married. You can't, you know, like you actually change into a different state. A less controversial application or whatever is when you have chickenpox. You're pre-chickenpox, then you have chickenpox, and then you don't have chickenpox anymore, but you are always somebody who had chickenpox before, right? And you can't go back to never having had chickenpox. You can have shingles. That's a different state, but okay. And yes, I realize by analogy, I've just made marriage chickenpox, but you know, hey, that's that's what it is. Okay, all right. And the latent state, like the cardinality of the number of latent states is usually unknown. Okay, so there's been a whole bunch of work for a long time on explicit duration Hmms or hidden semi-Markov models. Where the the latent state is also decomposed into a vector that has a particular that affects the transition probability from one state to the next. So each state, so the full latent state will be a sequence of tuples, each of which is a state identity, just like before. So S is going to be in some vocabulary again, and R is going to be in, I guess, Z plus. So this is basically the amount of time that you will remain in the state or have to remain in the state. So we have a latent state ID sequence, and then we have what we would refer to as the remaining duration sequence. And we have a state-specific duration distribution, in other words, how long you will dwell in the state, which is not necessarily geometric. You might choose Poisson or some other dwell time that's more appropriate to your application. Okay, you can explicitly say, the amount of time that one has chickenpox or has COVID or whatever is X amount of time. Like COVID is a good example. You don't have COVID, you have COVID, then you have antibodies, and then you can get COVID again. And there are specific amounts of time that you have these particular states. You can describe those times, they're known, you have a distribution over them, and you might want to be able to detect whether or not you have COVID or not based on, say, for instance, what's that sip and puff thing that you do when you, the oxygen reader where you like, who hasn't been pulled over by the police to see whether or not you're drunk driving?
The breathalyzer.
No, the medical version of that. See, now we know who has DUIs. Okay, there's the medical version of it, right? It's like lung capacity. You could like track lung capacity measurement over some time, and like that's your observation. And then there's a sequence of latent states, and you have a characteristic duration of poor lung performance when you are in a particular COVID state. Okay. Okay.
Can I ask? In a hidden Markov model, is the time is always discretized in like the same sort of step size, right? Like there's no sense of varying that time step.
Oh, this is a beautiful thing. So I am lazy and a terrible mathematician, so I never think about continuous time systems because I can't do stochastic, calculus. Basically, it's just like beyond me. So a couple of things. All right, a couple of things. One, I'm okay with that because computers are discrete time anyway. But I'm okay with that because we can change time in some sense by doing the following, right? We can change time. Oh, I'll watch this. It's going to be amazing. Okay, we can change time by discretizing time further, right? So like make the time delta t smaller, and then do this. That is a perfectly valid graphical model, and all the inference techniques that we're going to think about are going to apply, right? And in the limit, something funny happens, right? And you have to like put extra stuff in your calculus. So,
and people do that, but we're not going to do that.
We are not going to do that, but distinctly, definitely no. I hope that's not terribly disappointing for you. Fine, whatever. Okay. Okay, cool. So we're down here, okay? Fine. So an explicit iteration HMM or a hidden semi-Markov model transition between states in a different way than does a typical HMM, right? So the transition dynamics, and we'll do this mathematically in just a second or write it down. Unless the remaining time equals 0, the transition dynamics are that the state remains constant. It doesn't change. And then when the remaining time equals 0, then and only then does the HMM transition to a new state. Okay? So you can specify all kinds of different structural assumptions and priors about how the states relate to one another and which states you can get to and so on and so forth by putting zeros in A and by, for instance, doing exactly what we're talking about here. Okay, so
I have a
long
question.
story short, I'll say one thing and then Adam will take it. Long story short, when we're doing inference, regardless of what we're doing, we're going to have to do, particularly if we have, say, for instance, a Poisson distributed dwell duration or something like that, we're going to have to consider all possible states and all possible times, which may be unbounded in their support. And this is going to be something that I want you to think about. But anyway, Adam, go on.
Do you only sample the remaining duration time when transitioning between latent states?
Yep.
Okay.
So when you enter a new state, you also pick how long you're going to stay in it. So this is specifically the transition distribution here. So we have a latent state. It's a tuple consisting of state identity and time left in state. And this system tells you that is P of Zt given Zt minus 1. Okay, so the state stays the same if the remaining duration is greater than 0. Otherwise, you sample from the state transition distribution, and you when the remaining time is 0. The remaining time distribution is Dirac distributed. That really should be a Dirac distribution there instead of an identity function, but whatever, it doesn't really matter. Same thing. Yeah, I mean, let's just rewrite that as Dirac of R t minus 1 minus 1. That's what the distribution here is. And this one is Dirac of S t minus 1. Okay. So if the remaining distribution is greater than 0, you just count down. And otherwise, when the countdown timer is 0, you look at the new state that you've generated, and then choose amount of time to remain in that state. And then the observation distributions are exactly the same as before. Whatever state you're in, there's some observation. Fine. So the graphical model looks like this. Same kind of thing, still in HMM. And this is where I want to get you thinking about, like, the latent state can be some very complex thing that transitions in a super complex way. There's some observation, right? So this is Z2, and this is Z3, and the Markov structure of the graphical model is maintained, right? So there's actually just an arrow between Z2 and Z3, and from Z2 to Y2, and from Z3 to Y3, right? But there's a lot of internal structure. So all of the arrows, if you notice this arrow, this arrow, this arrow, this arrow, this arrow, they're just left to right. But inside, there is a little bit of extra structure. No big deal. It just means that Z is structured. It's a structured random variable. And I already hinted at the fact that graphical models can sort of be graphically recursive. So you can have a graphical model inside of a node in a graphical model. So Z here is some vector object, but its distribution is governed by a graphical model over the internals of that vector. Okay. Fine. And same, so these are the, dwell duration distributions. They can, so on and so forth. These are the next state distributions as before, and these are the parameters of the likelihood, the observation distributions. Fine. So chickenpox, this is an example of a left to right HMM, which is structured. So you have vital signs, latent states are pre-infected, infected, post-infection, state transition. You can't go from infected to pre-infection, disregarding shingles. Structured transitions implies zeros in the transition matrix. So for a left to right HMM, well, these are called left to right HMMs anyway, the probability of transitioning to some state M, given that you're in state L, is 0 for all states that are in index value less than L. Okay, so we can have structured HMMs, we can have structured explicit duration HMMs, so on and so forth, all these things. Structured HMM looks like this in the trellis form. Basically, you can only transition in this direction. You can't ever transition back. Okay? All the other edges are 0. We're going to go a little bit further. So this is like, HMM, structured HMM, explicit duration HMM, so on and so forth. Bayesian HMM. So normally you would run forward backward. What do we call it? It's forward back. You'd run expectation maximization using forward backward for marginalization to learn parameters, but you can also, and this is what we'll do in this course, talk about Bayesian HMMs, where we put a prior on the parameters so we can affect a solution that conforms to our ideas about this, what the solution should look like. We can put structured priors that specify hard constraints, or that certain states are more likely to transition to others than what other. The automatic regularization you get from Bayesian regularization means that we can actually specify a model with way more parameters than could possibly be needed. So an easy way to think about this is if you are trying to learn an HMM, like actually learn the transition distributions and emission distributions given only data, which is something we'll talk about in the course a lot. You can just specify a large number of states. In fact, you can actually derive the limit of HMMs as the number of states goes to infinity. So you can automatically learn the number of latent states in an HMM, avoiding lots of model selection issues. And you can think of them as being auxiliary nuisance variables. And inference in these models requires sampling procedures that can deal with countably infinite support, which is the subject of inference in higher order probabilistic programs. Okay. And the posterior of the latent variables in this particular case encodes uncertainty about the interpretation of data. Okay, so a Bayesian HMM says actually now we have some distribution. These are going to be specified, generally speaking, over the transition probabilities. So what would HZ naturally be? You should all know this from working on the homework. If pi is a probability vector. What's the distribution over probability vectors? Okay, it's coming in the chat channel, at least 2. All right, Dirichlet, awesome. So this would naturally be Dirichlet, but it could be even nastier. Theta, if we have a discrete one-hot vector output, would be nicely Dirichlet or discrete. Rather discrete, or if you have a real valued vector, it could be normal, or it could be a normalizing flow, or it could be whatever you want here, right? Great. So the point though is that these now are also latent variables, and we want our inference algorithm to infer given y, not just the latent state sequence, but also the state transition distributions and the transition distribution, the observation distribution parameters. Totally fine, no issue. I feel like there's a question coming in the chat that I can't see, but it's being typed. Is that a correct impression? No, okay, good. All right. You can go further, right? You can build infinite HMMs. You can build sticky infinite HMMs. We'll be able to code all of these things relatively directly in our languages, so we're not going to go into a lot of detail here, but you should be aware that there are priors, structural priors that you can stick particularly on this that allow you to have an infinite number of states, okay? Which is kind of cool. And this relates to what we were talking about in that these infinite HMMs and the explicit duration of HMMs that we are going to talk about share a fundamental characteristic, and I think it's easier to talk about that characteristic in the case of explicit duration HMMs because I don't have to explain Dirichlet processes and hierarchical Dirichlet processes and how to do inference in those, which is like an entire course. But we can talk about the inference techniques that one would have to use in the EDHMM, basically using the tools from infinite HMMs. And you get a nice approximation-free, efficient inference algorithm for EDHMMs. Okay, and you can try this in your application, so on and so forth. Okay, so let's probably pause relatively soon, which is kind of annoying because there's still a lot to go. And I want you to think while you're munching or doing whatever it is you're going to do during our agreed upon break. Let's think about the inference challenge. So we kind of know a couple of things at this point. We know how to do Markov chain Monte Carlo. We know how to do Metropolis Hastings. We know how to do Gibbs, and we know how to do Metropolis within Gibbs. Okay. But let's say, for instance, that I'll just go ahead and put this on here as well. I don't think I did this. This is kind of silly. RT is Poisson lambda. M. Okay, I should really make that a little bit more precise. RT given ST equals, yeah, okay, I got to do the whole thing. ST equals M and RT minus 1 equals 0 as Poisson lambda M. Okay. So let's take a little break, and I want you to think about what the problem is here and how we deal with the inference problem. So let's see if we can figure out what the inference problem is from in particular, Gibbs sampling perspective. And then let's think about how we could solve it. Okay, I'll see you at 4:32. And we're back. So what's the problem? GameStop. That's the problem. The problem is here. I'll give you a hint. The problem starts with this. What's the what values can RT take?
Oh, it's unbounded and real valued?
Not real valued, integer valued, but unbounded. Correct. Yeah. Which means that there are actually how many states?
Infinitely many. Infinitely many,
right? So if you were to, for instance, try to, I mean, there's lots and lots of problems. Like there's lots of huge numbers of problems in performing inference in this model, and we don't have enough shared common understanding yet to really go into all of them. But the one that we're going to talk about right now is the fact that in fact, if you go back to the trellis view of HMMs, right, that there was one trellis position for every latent state, right? But in this particular case, Z is the tuple of the state and the remaining duration. So you have a finite number of states, but you have an infinite number of possible remaining durations, which means that in fact, the tuple Z has infinite cardinality. Okay, now you're totally screwed, right? When you're doing Gibbs sampling over the state of Z, you can't possibly enumerate all of those values, right? And if you try to And if you try to do other kinds of inference algorithms, you'll figure out that this system is incredibly stiff. It's very, very difficult to do inference in, not least of which is because you actually have to, like when the system is stiff because there's discrete transitions everywhere. The system is counting down, and you have to be able to transition simultaneously several values at once in order to actually get a consistent sample. So Gibbs sampling won't work, and even if you could Gibbs sample, you would have an infinite dimensional state space that you'd have to enumerate over, and all sorts of horribleness. Okay, there was somebody who was going to ask a question or make a statement.
Question.
Yo.
So when you say RT is unbounded, does that mean big T can go to infinity? Or
no, sorry. I'm saying I will usually when there's big T, I will say R big T or R capital T or something like that. So I'm saying that the support, technically I'm saying the support of every single one of these little RTs, R little t, like if it's Poisson with some rate, we have a discrete distribution with some rate, and there's non-zero support all the way to the right under a Poisson distribution.
Okay. So R little t can take on infinitely many discrete values.
Correct.
Okay, but there is a finite number of R's.
There's a finite number of S little t's. So there are a finite number of little states. So there's like you have had chicken pox, you've not had chicken pox, so on and so forth. But if the duration that you choose happens to be Poisson or something like that, Poisson distributed, then you have an infinite set of durations that you might have to consider, which means that the joint state is like chickenpox for 1 day, chickenpox for 2 days, chickenpox for 3 days, chickenpox for 4 days, chickenpox for 17,000 days, right? I mean, you could have a really crappy, whatever. Okay, fine.
Can I ask a question about this?
Yeah, totally.
Would it help at all if you were to just sort of bound the total amount of time that this is allowed to run for? Say you sort of set a restriction on the sum of R. So you sort of say that, like, it's kind of like setting a T in a sense, maybe, right? Like, but instead of setting a T, you're just setting like, okay, my algorithm has to return in like this amount of time steps.
I think so. One of the old school approaches to this is to say that no particular state occupancy could ever go beyond some amount of time, which basically renders the total number of states finite, and then you can run typical forward-backward inference algorithms. But that's not actually doing inference in the model. It's doing inference in an under approximation to the model. So we're going to talk about techniques for doing this. And really, the take home here is really two things at this point. One is to get you to realize what it was like when we, like this is the result of a lot of thinking, like 6 months of thinking to figure out how to do inference in this model, right? So we're like, how do we do this? And in the process of explaining how we do inference in this model, I'm going to point you at a couple of little tricks and techniques that are pretty cool. And the biggest one that just kind of slides in there in a kind of a nice way is slice sampling, which is a very, very powerful general technique. Okay, so this work basically is all about like, okay, we've got this problem, we want to do inference in this model. And in fact, we were given this as a challenge problem by electrical engineers. And it's really unfortunate because there's some electrical engineers that have been asking to work with us, and I forgot that I even did this work. But the electrical engineers wanted to be able to do some testing on like spurious voltage transitions in nanoscale transistors, and they knew something about the state dwell times, something from quantum mechanics. They knew how long things are supposed to stay in particular states, and they wanted to be able to do inference to be able to count the states that their various transistors went in under experimental conditions really, really fast. And it had to be super accurate. It had to be interpretable. Okay, so we actually did deploy this in that setting, which is kind of fun, and I'll show you some results for that later. But anyway, so what we did is we said, oh wait, actually we have this uncountable support problem. Or countable support problem, excuse me. Countable support problem. So this looks like an infinite HMM, and by the way, there happens to be this lovely piece of work by Jürgen van Gel out of Zubin's Germani's group at Cambridge, where they developed a forward filtering backward slice sampling approach for the infinite HMM. And yeah, so we're gonna use that, okay? And it looks like this. But let's talk about slice sampling by itself for a second. This is a super cool idea, and it's when the first time, none of you have seen it, so, and this is a project idea. You can actually, nobody's ever done this. I don't know why. It's unbelievably stupid that nobody's done this for general purpose inference for discrete random variables in probabilistic programs, okay? I just have been too lazy to do it myself. So forget the HMM for a second. Let's say that we want to get samples of X, and it's governed by some distribution with parameter lambda, okay? Fine. So sometimes, oddly, it's easier to introduce an auxiliary variable u and to then Gibbs sample the joint distribution. And we know that Gibbs sampling just alternates sampling from one conditional versus and the other conditional, so on and so forth. So in other words, sample from X given u and lambda, then u given X and lambda, and back and forth, right? And then just marginalize by throwing away the u values to get a sample of X than it is to sample directly from P of X given lambda, okay? Take it out, I see Vasilios rolling his eyes like, what, huh? So just take it on faith for the moment, right? That this makes sense, okay? So this can be useful when P of X given lambda doesn't have a known parametric form, but adding u results in a parametric form, or P of X given lambda is something that you only know up to a normalization constant, but you can smack a term on front of it such that it becomes a normalized distribution, and then you can sample from it. There's all sorts of reasons why you might do this. And when X has countable support, and sampling it requires enumerating all values, okay? And that's what we'll talk about right now. Okay, so the pedagogical example, which happens to apply in the EDHMM case, and in other cases, so there's a whole bunch of slice sampling for Gaussian processes and so on and so forth. Some relatively famous work from Ryan Adams and Ian Murray. But let's just do this because it gets the basic idea across. So let's say that X is drawn from Poisson lambda, okay? Countable support, or we have some distribution with countable support, hand. I don't understand why sometimes you use hand and then sometimes you just talk. The hand is hard for me to see, so just talk.
Well, you were in the middle of talking, and so
That's fine, doesn't matter.
So on the previous slide, when you say you introduce u as an auxiliary variable, can it be like anything, or do you have to does u have to be picked intelligently? So the
whole point in any auxiliary variable sampling trick, technique, whatever, and we'll do Hamiltonian Monte Carlo, and that's the granddaddy of auxiliary variable tricks, grandmother or whatever. I don't mean to be gendered in that. The whole point is picking very precisely, thinking very hard about what the form of that additional distribution will be, and I'm going to show you an example here. Okay, so indeed. The point is that if you think about it from a graphical modeling perspective or a joint distribution perspective, you can see that like marginally, if you just marginalize out u, immediately you have the distribution you want. So that's the only thing that you need to think here. And here we're going to give you an example where this is case. So let's say that we need to do Gibbs sampling, for instance, in the space of Poisson distribution for whatever reason, right? This isn't Poisson, but this is some other distribution with countable support that we don't know how to sample from. That's really what you should be thinking, okay? So one way to do it is to just enumerate every single possible value, compute its likelihood, and then sample according to that distribution, right? So that's the enumeration strategy that you have theoretically done in the homework. You just enumerate everything and pick, right? Can't do that when the support is unbounded, right? But you can introduce this really weird auxiliary variable with a crazy distribution. So P of u, this is the auxiliary variable we were just talking about, given X and lambda, has the following density, okay? Which is 1, so this is just a uniform distribution. It's 1, and it's 1 in the range to the density of to the density value of P of X given lambda. Okay. That make sense? So it's 1 there, 0 everywhere else. It's 1 when it's between 0 and p of x given lambda, the value of p of x given lambda, 0 everywhere else.
So if you were to draw the Poisson distribution here, would touch on the upper right-hand corner of that that sort of block, right?
No Poisson distribution. I'm just looking. This is p of u given x and lambda. This is, yeah, u on the horizontal axis. So it's a uniform distribution from 0 to p, the value of p of x given lambda. Okay, the number. It's hard to grok right away. Okay, but we'll get to it. Okay, and here's what happens. Right, the marginal distribution of x given this particular choice, we can just write it down. Right, so we're gonna take p of x given u. We know this is just marginalizing over u. We could write an integral here just as well. That doesn't, we're being sloppy about this, but we're going to marginalize out u. Payment is right. It's 1 over p of x given lambda. That's the value at the top. Yeah. So that when you multiply the two edge lengths together, you get 1. Exactly, 100%. You're totally right. Thank you. Okay, so we're just going to marginalize out u, right? So we know how to write down the joint distribution. I've just given you the joint. I have p of x given lambda, whatever that happens to be. You can think Poisson. That's fine. But I'm going to take this and just write it down here because that's the joint distribution. That's what the structure of the graphical model is, first of all, and then that's what we've just written down. So I'm going to plug in this definition for u. Right? These terms are going to cancel, and this is going to basically integrate over u from 0 to it's going to integrate 1 from 0 to p to the value of p of x given lambda, which is equal to p of x given lambda. Okay, weird. Okay, so why would you do this, right? Hopefully it's in the next one, okay? Yeah, so this suggests a Gibbs sampling scheme, which is kind of interesting, right? It's actually really interesting. And like, this should totally just be mind warpy, particularly for people who've thought about this for a little while. It suggests a Gibbs sampling scheme where you alternately sample from p of x given u and lambda, so p of x given the slice and whatever its parameter is, as being uniform. It's just 1 for every value of x for which the density is above the slice. The density evaluation is above the slice value u. So like literally take a slice and just pick uniformly amongst these values. Okay? And then you have a conditional distribution. You have the conditional distribution of u. You take the value that you have, right? And you draw from that distribution. There's a uniform distribution basically under that value. So you're going to draw somewhere here. And then you're going to draw a new slice. And then you're going to enumerate, so on and so forth. Okay. Okay. Then you just discard the values of u, and you get x samples marginally distributed according to p of x given lambda. But you will never have had to enumerate the infinite set of values. Everybody think you could go off and implement this little slice sampler right now? No. Okay, why not? Might as well make sure we get this even if we run out of time. This is actually a more interesting thing.
I'm confused why there's R of t in the bottom here, so I'm not sure I understood.
Oh, sorry, this R of t, yeah, don't worry about this. This is x in this. It's going to be the remaining time distribution in the EDHMM. That's why it was R of t. Sorry, yeah. Okay. So yeah. So here's the Poisson Pdf evaluated at x and lambda equal 5. Okay, this goes off to infinity, right? So you can draw a u. You can start with a u. You initialize your Gibbs sampling. You start with a slice variable. And this says, I don't know how to say it any other way other than when you go back and stare at it and look at it, right? So what have we done? Let's just go back really quickly. We want to draw from this distribution. Okay. But we don't want to have to enumerate. We're going to have to enumerate in a subsequent sampling step. You'll see why in just a little bit. Basically, if you're going to do a Gibbs sampler, you need to be able to enumerate, or if you're going to do a forward-backward algorithm, you need to be able to enumerate over your states. Okay, so we don't want to enumerate an infinite over an infinite support. So we form a joint distribution of this form. We choose a particular auxiliary variable distribution which marginalizes correctly, which means that we can Gibbs sample in the joint, and we have samples from the thing that we want. And what we're showing here is literally just exactly what this describes, which is sampling according to the individual conditional probabilities, right? So the conditional probability of x given u and lambda under this model is just this indicator function. So it's uniform above the slice, finite support, uniform above the slice. You can enumerate. And then you sample the slice variable from its conditional, which in the graphical model is already given in this way. Yeah, that's it.
So is lambda fixed but not, like unknown?
Lambda is fixed, and in this particular case, it's going to be given to us. Yeah, absolutely.
Okay.
Ultimately, in the EDHMM, in the Bayesian EDHMM, it won't be. We're going to do inference over lambda as well, but that will treat that as a separate Gibbs sampling step. I'm not going to do out the entire. In this, I said basically all we're going to focus on is doing inference over the latent states Z, of which one component is this R. But the slice sampling thing is like you set a slice, you enumerate above the slice. In other words, you sample uniformly above the slice, and then you sample the slice conditioned on the density evaluation of the sampled x value, or going to be R in just a second. Okay, crazy. Okay, I can see that we're not entirely getting this, but that's okay. Hopefully, you'll hang on and you'll maybe see it later, or you go back through it and so on and so forth. I also am using this as remember the point is to introduce you to slice sampling and to convince you that you want to do probabilistic programming, because if somebody gave you, the transition, said, here's some data and I want to be able to count the transitions in a nanoscale transistor, and you have to use a hidden semi-Markov model, go build an inference algorithm for that. It's hard going, okay? As you've already seen in the homework, but this is like, I'm giving you a lecture on one, and even just like a lecture on one is like, oh my God, what is this stuff about, okay? And we're gonna Prob Prog is gonna make this much, much easier. Right? That's the whole thing. We're gonna start doing Prob Prog next time, okay? So this should be the end of, oh my God, this is horrible and hard. And then we'll start talking about, this is gonna be easy and automatic, just a second. So when we do this auxiliary variable trick, the auxiliary variable tricks depend, in the EDHMM, we can use this auxiliary variable trick by basically imposing an auxiliary variable u that has the following connections, and we'll talk about exactly what this is. So we can impose auxiliary variables that are defined in this way, which are conditioned on the value of the state before and the state after, which involves both R and S. So when you evaluate this, you have to be evaluating expressions in both P of R and P of S given R and so on and so forth. Are beams slices?
Just wondering, because this slide says beam sampling, but before you were talking about slice sampling.
Yes, thank you. Okay, wonderful. I'm glad that somebody is reading the text on the slides. Probably should be me, but that's fair. So slice sampling really refers to the trick that we're talking about here. Beam sampling, as it will occur relatively soon, is you can basically you can think of a path, like one particular sample path through latent space, as being a beam. So if you've ever heard of beam search, it's the same, and Vasilios could tell you more about beam search than me, but basically when you thread a a beam. It could well have been called thread search or or whatever. A particular sequence, one setting of the entire latent sequence is a beam. Okay, so we're going to use slice sampling to do beam sampling. So we're going to use a bunch of slice sampling variables to specify a set of beams that we can actually consider. And then condition on the beam, we're going to sample our slice variables and back and forth. So we have these auxiliary variables that are defined in this particular way. So we have an auxiliary variable defined condition on the state, and again we have to evaluate these. We have to evaluate the R and S a little bits, right? In particular, P of Z given Zt given Zt minus 1 is the probability of the tuple given this tuple, and it looks like this, right? There's it's 1. If if it's counting down and you stay in the same state and you've counted down by 1, otherwise it's given the value of this, where you transition to a new state and you pick a remaining state distribution. Okay. Whew. All right. So here's where we could use many more lectures for those of you who do not have this background. But again, we're going to do Prob Prog, so it doesn't really matter. And we can't do forward backward in the Prob Prog setting, so don't worry about it. Like, just be aware that there's a forward backward algorithm. But condition on the U's, we can run forward backward. And this means that we only need to consider a finite number of successor states in each time step. And what does it look like? We can do this, and hopefully we can get through this, and then I'll show you some examples of what this looks like when we do it. There's a forward backward algorithm which allows you to marginalize the latent state distribution in an HMM, and allows you to do parameter learning via EM and all that sort of stuff. But here we're just going to do it sampling. So here again is more custom sampling thinking. So we need to build this what we would call a forward message, which is the distribution of Zt given all of the observations, and in this particular case, given all of the values of the slice variable. So we're basically setting up a Gibbs kernel to sample at the end. Actually, what we really care about sampling from this is Z capital T, capital big T, given Y1 to capital T, U1 to capital T. Okay, but it turns out that we can get to this distribution via a finite polynomial time computation by making use of the slice variables. So to get to here, we just need to marginalize. We're marginalizing over everything, but if we had this distribution and we just marginalized out Zt minus 1, we'd be okay. But if you look at this and you sort of start peeling off the conditional factors according to the graphical model, we know that there's a UT from the graphical model just here. There's a UT that sits in between Zt minus 1 and Zt, and depends on both of them. We've just given you the density for that. And this just is the remainder after you throw away stuff that is blocked by d-separation. Right. All right. Then we can further break this down into a likelihood term, a probability of transitioning, and this other thing here. Okay, fine. And if you combine this with this, by the definition of this, what's left is this indicator function times a likelihood times a recursive thing like this. So we are able to use a computation, a polynomial time computation, to compute a very, very important marginal distribution. We can actually marginalize and sample from Zt given everything exactly, because we can actually compute this value. Okay, Z big T, that is. Okay? So the last latent state. Fine. We can get a beam. We can actually recursively sample backwards by looking at what the probability of Zt minus 1 is given Zt, Y, and U. That's proportional to the joint of all of those things. That's proportional to all of the Markov model factors times the incoming message. That's what's left. This is again like so, which means that we can sample basically, at the end of the day, we can run an algorithm to compute a marginal distribution of the last state and then sample backwards according to this backwards chaining recursion where we use the forward messages in the first place. And we only have to ever consider sampling Zt minus 1s that lie above the slice. So we never actually have to enumerate. Okay. And you can probably see that once you have, this should be a good Gibbs sampling question, right? So we've run forward. I've told you how to sample these. We've run forward, backward, and I've told you how to sample all of the intermediate all of these, right? Now, once you have those, sampling the slices is going to be very easy because you know the distribution of the slices, so you can Gibbs sample the slice. So you can run forward, sample backwards, Gibbs sample the slice. Condition on the slice variables, run forward, run backward, sample the slice variables. Run forward, run backwards, sample the slice variables. Okay, fine. And that gives you basically the complete algorithm. So you run forward to get these forward messages given the slice variables and you sample backwards Zt given the last message, and you go backwards sampling according to this, where you don't have to enumerate all possible states because you're using your conditioning on the slice variables. Then you slice to slice off the beam basically. And you effectively evaluate the densities that you need in order to sample the slice variables. And then if you're doing a Bayesian EDHMM, once you have the states and you have the slice variables, you can then go off and sample using whatever your favorite sampler is, the parameters of your transition distribution, the parameters of the duration distribution and the likelihood distributions. Fine. And you can do posterior predictive inference, so on and so forth. I think we're over time, so I will get to the meat of it. So we've started with some crazy HMM. We started with regular HMMs, then we said, okay, we want explicit duration HMMs. Unfortunately, they have an infinite number of states if you use sort of normal dwell time distributions. In order to actually sample in such a model, you have to derive a custom inference algorithm. In order to derive the custom inference algorithm, you have to figure out what slice variables are, and then you have to figure out how to beam sample above the slice, and then you can do a Bayesian HMM. Great. But at the end of the day, you can say, okay, we have 4 states with some characteristic dwell distributions. You have Gaussian distributions with means given by those parameters in all unit variance. This is one dimension. And you can ask what the posterior distribution over the state means, which are given by these red points, and the transitions between them with the characteristic dwells. So this does well on synthetic data, obviously. This is the posterior distribution over the dwell times that you get from running a big Gibbs sampling chain. So they're centered on the correct values. Fine, no big deal. The duration rates. So in other words, there's some posterior distribution over how long the states are. These are also centered on the correct dwell times. And you can apply this very specifically in a very nasty application, which is this nanoscale transistor spontaneous voltage fluctuation problem, where the scientists know what these characteristic dwell times are, right? And what they want to be able to do is automatically count when the transistor is in one of these 4 states, 0, 1, 2, 3, something like that, right? And in order to count that in this kind of data with an HMM, you have to impose incredibly strong prior knowledge in order to actually get these little wiggles not being absorbed by, for instance, the likelihood terms. Okay, and you can even do crazy things where in such systems you can have states that have exactly identical emission distributions but different durations. And inference in such systems, in such a model, will actually be able to distinguish the states just by their dwell times. So a nice example application of this is, in fact, looking at the Morse code Kepstrom, basically. So here is the spectral decomposition of Morse code, right? So there's dots and dashes. Here's a dot, here's a dash, here's a dot, here's a dash, right? In a particular time slice, you can't really tell the inside of a dot from the inside of a dash. They're exactly the same, right? In other words, the emission distribution basically is the same for the two. The dwell time, however, is not. So this is an EDHMM, a Bayesian EDHMM fit to Morse code data, and it automatically learns to distinguish the fact that there are two states with the exact same emission distribution, but different dwell distribution. So the state is characterized by that. And this is actually just an infinite HMM, which was kind of the state of the art at the time. So that's the end of this horror of a lecture. And it's meant to be a horror of a lecture, basically to drive home the point that if you want to write down these kinds of models and you want to do custom inference for them, deriving custom inference algorithms and thinking about how to build custom inference algorithms is a non-trivial intellectual endeavor, more or less, right? I wanted to firm up a little bit about what HMMs are and what applications there are for them and how they relate to Prob Prog. I wanted to introduce to you the idea of auxiliary variables. You should look at these slides and sort of like grok what's going on. It's really pretty cool. And slice sampling, and just to give you a sense of like what probabilistic machine learning was like before probabilistic programming. And it's still quite useful, in particular when you want to be able to inject knowledge about the underlying problem, right? And that can be difficult to do in some modern applications and more modern techniques. So with that, I leave you for today and will take questions for those of you who wish to remain and ask questions. Thank you very much. No, not so much applause, really. No, that's too much. Just kidding. Questions, please. Questions, conversation.
I have a question.
Surprise.
So going back to the auxiliary variable, way back, would a real world example be, say, like we're taking the context of question 2 from the homework with the cloudy sprinkler wet grass, we are having trouble determining if the grass is wet, and so, or determining if it rained, given that the grass is wet. So then we add in this auxiliary variable, like, are there worms? And because like worms might indicate that there was rain. I don't know. I'm trying to find like a real world example of what an auxiliary variable could be.
So I mean, an auxiliary variable, there's nothing fancy about an auxiliary variable. It is literally just a latent variable that's that you don't care about. It's a nuisance variable. So why did they refer to them as auxiliary variables? They refer to them as auxiliary variables as sometimes you can introduce a nuisance variable that gives you some advantage. And we'll see this. Sorry to just say we're going to see this again in when we do Hamiltonian Monte Carlo, but we're going to talk about Hamiltonian Monte Carlo, which is a gradient-based inference algorithm where you will be able to where you'll want to impose like an auxiliary variable that is basically allows you to think about a generalized momentum, to give a particle actually like a momentum, and it allows you to explore a sample space more efficiently. A real world example of this it is of these kind of slice variables, the utility of them it's difficult to do in the homework 2 example, because you don't have there's not an easy place to put an infinite number of states in there. But in the LDA example, you could relatively easily think about situations in which the number of topics is incredibly large.
I'll just think about it some more.
The unfortunate thing is, relative to a real world example, this is probably the best real world example of a situation where you want to use slice sampling. That's why I actually chose to talk about this rather than some other like crazy inference setting, or when you're doing Bayesian nonparametrics and you have infinite cardinality models. But for now, just think of it as a way to get around the fact that you may wish to do inference in models with infinite support. And if you need to, like, I guess you're doing Gibbs sampling and you can enumerate, but maybe in the wet grass example, let's think like could we actually change that easily right now to be yeah, I mean, if you think about a problem in which, say, for instance, you have an amount of rainfall, just for the fun of it, right? And you have this is like, let's say this is X is the amount of rainfall. And this is how wet the grass is, or is the grass wet or not, right? Just whatever, grass is wet. And let's say that X is indeed Poisson distributed, and this is now Bernoulli with some likelihood given by a function of the Poisson value, wet or not, right? If you want to Gibbs sample this thing, right? These are not conjugate to one another. So like a Poisson and Bernoulli are not conjugate to one another, which means that you actually don't have a closed form expression for how to sample from X, right? Okay, so which means that you basically have to do Metropolis within Gibbs, or you have to do some sort of slice sampling trick in order to actually keep from having to enumerate an infinite number of possible amounts of, I'm saying integer amounts of rain, like 1 inch, 2 inch, 3 inch. I know you're American, so I'm using inches. 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, something like that, right? I think you're American. Are you American? You went to the University of Washington. Are you Canadian? Oh, I'm very sorry. I know you went to the University of Washington. That's all I know. So never mind. 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters of rain. Those are the only options that you have under a Poisson distribution, right? But if you want to figure out, given that the grass was wet, what the posterior distribution over the number of centimeters of rain that you had was, and you want to do it via sampling, and you think about it for a second, like you can't Gibbs sample that directly because you can't derive the posterior distribution directly because there's not a conjugate relationship. You would have to do some sort of Metropolis Hastings thing with a nasty transition kernel, which is like +1 centimeter, -1 centimeter, or something like that for Q, or you introduce a slice variable. And when you have a slice variable, an auxiliary variable, you have a slice variable, then you can say, okay, I'm just going to sample above and below the slice, and I'm going to sample this auxiliary variable, which I've introduced just to keep things finite, basically. So that's how you would extend, for instance, even the grass is wet example with an infinite support kind of situation where writing down a sampler in other ways might not be as efficient. Yeah, I think that's about as good as I can do right now. I don't know if that makes any sense. Try it out, you'll see. In terms of a project, just to be clear, in the FOPL context, like dealing with discrete random variables and like deploying slice sampling in order to control the complexity of control flow is something that has not been done, which is very silly because I think it's basically straightforwardly applicable. So that's on the order of an easy project one could consider doing, and might even be publishable. Just to throw it out there. More? Everybody has a question, and everybody's just waiting. Sorry, Emma. Everybody's just waiting for you to ask another question to get more information. That's what's happening. It's really maybe we should just pay you to be the TA at the moment, right? That's like somebody else. There we go. And you're good for the second question. That's good. Yeah.
So we were discussing like the simple example of HMMs, and then you mentioned that you could think of them as being mixtures of Gaussians, or just mixture models.
Marginalizing over time. Marginalizing over time, they are.
Okay. If the HMM is not ergodic, is that an issue? Or
here, this is why I tried to distinguish between what we talked about before, where we were designing Markov chains in order to have various properties and allow us to explore the entire space and that sort of stuff. Here, we don't care, right? And very specifically, right? There's the left to right. When we're talking about left to right HMMs, this one right here, this is an irreducible Markov chain, right? It has absorbing states. In particular, state 3 is an absorbing state because you can only move to state 3, right? And this is a desirable characteristic of certain state transition mechanisms, because certain state transition mechanisms, like disease progression, actually are this way, and you want to model it. So the stuff about ergodicity and aperiodicity and detail balance and all that sort of stuff that we talked about before don't apply here. We want to have a model of the state transition, and we want the states to be indicative of something that we care about in some applied domain, like, for instance, the identity of letters, or whatever. Yeah, that makes sense.
Yep.
Great.
I have a general question about HMMs and like applications. So, like, if you are there any cases where you would want to have undirected, like, graphical model kind of thing for like transitions between states? So like
Did you say undirected graphical? Did you say undirected graphical model?
Yeah, like in the form of HMM, like where you have like undirected edges between state transitions.
Yeah, for sure. Yeah, I mean those are called conditional random fields, and they've been around for a really long time. And the resource to look at for those is UMass Amherst. Andrew, come on, you can help me out. I think Vasilios, you should be able to do this. Conditional random fields. You're like an NLP person, so you should know. The faculty person in Edinburgh moved to Google. Charles Sutton and Andrew McCallum. Conditional random fields. There's a whole tutorial on conditional random fields.
Okay. Yeah, I was just thinking, like, for speech recognition, like, would it be better to use conditional random fields? Because, like, for example, sometimes you can have this kind of like dependency on the future also, right? Not on the past.
Yeah, so the conditional random field doesn't give you that unless you actually have edges, because in an undirected graphical model, you can read off independence directly from the model, right? Conditional independence, and conditional independence is like, if you're not directly connected, you're conditionally independent. So conditional random fields by themselves don't actually give you long-range dependencies. It doesn't actually help you.
Okay.
And modern deep learning systems would indicate that actually sort of RNNs type models, or HMMs, in which, if I go back to the graphical model for just the plain HMM, let's not forget that if you right? A complete factorization of a joint over the latent space simply means that you have to have, you know, this edge and 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 so on and so forth. And the name given, the models that have this characteristic, there's a bunch of them. The last one in the world basically that was in the pure probabilistic non-deep learning framework, it's called sequence memoizer, and that's mine. And as I was telling people earlier, like that's you know, unfortunately that happened at the same time as deep learning happened, and then basically it just got blown away because deep learning took over. And the other one that has this characteristic very explicitly is the variational RNN. Or in fact, really not even a variational RNN, that's the probabilistic variant. It's just an RNN, right? So like people who know HMMs, if you say this transition is deterministic, then a couple of things are true, right? Then you can basically think, there's a couple of ways of looking at this from a graphical modeling point of view, and this is actually kind of important because this is just leaning to the future, right? If it's deterministic, then effectively Z0 to ZT is just one big random variable, and you have a bunch of observed hanging off of it.
Okay.
That's the RNN case. And if you have a variational RNN, then the ZT actually factorizes like what we've been looking at in that there is a backbone, I guess we'll call it C, and then a random variable which we can call Z. Probably can't see that. I'll do it again. Basically, the latent state factorizes basically what I'm trying to say. There's CT, which has a deterministic transition, and then there's a ZT plus 1, which has and a ZT, which are the stochastic elements. And this, just like the ED HMM that we talked about, this tuple is the state in an HMM, and the variational RNN, because of the fact that these edges are deterministic, they're Dirac distributed, which means that when you do the integrals for computing forward, backward, or so on and so forth, you just plug in the values. There's no distribution there at all, right? Then what the variational RNN gives you, and the reason why it's super powerful, is that it gives you all of these edges.
Okay.
It is a fully connected graphical model, which means that it is capable, in principle, of representing the joint distribution to an arbitrary level of precision over all of the Zs, right? Okay. This is what the pixel CNNs are about. Basically, all of the recurrent architectures effectively are HMMs where all of these edges exist.
Okay.
That's also, just to be clear, like what Prob Prog is about. Like Prob Prog, when at the end of the day, even though I'm saying that it's a Markov transition like this, another way of looking at it is that it is just an HMM in which every single edge can be there, and you weed out some by eliminating variables, like by however you write your program, basically.
Okay.
This is a bad sign. I've even forgotten how to say ege. Is that right? I'm just gonna, you're being very. I want to make sure that I get. So like, who haven't I heard from? I haven't heard from Namrata, and I haven't heard from Ege. So either that means that you understand everything, or you're totally happy, or whatever. But I do want to know who you are and like get some stuff.
Yeah, trying to understand everything. I will get there. Yeah, I'm happy with the questions that I was asking. Will add my own questions soon enough, I guess.
Okay, please. I just want to make sure that you're getting your money's worth, as it were. And Namrata? Chicken. Okay, let's see. I don't think, actually, now that I see it, I don't think we've heard from Ina today either. I think she's been dead silent.
I don't know what to ask.
You don't have to ask anything. I just want to make sure you're okay. Like that's it's like the nice thing about having a small group. We can actually like check in with each other, right? And get to know one another. So
I'm looking forward to the next lecture because you said it's going to be easier.
It should be. Let's see. I don't. Should we find? I don't know what is the next next lecture.
And keep in mind that we have these recorded.
Oh yeah. So there's okay. So you can use this to blackmail me if I'm. Okay. I don't know why this is not. Oh yeah. So what is the next one? Oh yeah. Yeah. This is going to be awesome. Oh yeah, super straightforward. Yeah, great. It's the end of part one, though. That's good. So now theoretically, you know everything there is to know about inference. You're totally set with old school, old style inference, enough to be dangerous. And now we're going to make it so that you can perform inference in any of these models by first writing them in an interesting way and then developing general purpose inference algorithms. So yes. Particularly if you're a computer scientist, now we're going from statistics now to computer science, like much more computer science. So if you're into the computer science thing, then the next part is going to be really easy, and the statisticians and mathematicians are going to be like, what in God's name is going on? So no, it's much easier now. It'll be easier. Cool. Anything else? More questions? That's great. Awesome. This is wonderful. Awesome. Okay. Go for it. Yeah.
Which of us?
Well, since you were speaking, I don't know. I think it was Berend, Adam, and Emma. Yeah. So I don't know. Adam, Berend, Emma. Is that okay?
Yeah, it's also me. Okay, I'll be the one.
Oh, sorry, Greg.
It wasn't me.
Oh, sorry. Like Zoom. They all came in at the same time. That's, yeah.
Okay.
Adam, Greg, Emma.
I'm wondering if there's been any work done in Prob Prog using stochastic calculus, the same way there's been work done on stochastic neural ODEs.
Not that I'm aware of, honestly.
Okay.
Yeah, not that I'm aware of. It would be something to yeah, no, I have no idea. Yeah. Good question. Good idea. Greg?
I have a question about LDA question in the homework. So like, do we need to derive all the like the collapse, like the do we have to integrate out like all the parameters and show the derivations and for everything, or can we just find all the formulas in some book and code it up and call it a day?
The point is not to force you to do all of the multinomial Dirichlet derivations, but is to force you to recognize that those things are available and you can look them up in a book and know how to look them up in the book. So you can either derive them if you can't figure out how to look them up in a book, but if you know how to look them up in a book, then you can look up the conditional probabilities that you need and use those conditional probabilities for sure. Yeah.
Okay.
But it's more an exercise to make you understand like the mechanics of, okay, here's a joint distribution, here are the conditionals that we need. When I see the conditionals, they have Dirichlet, they have all sorts of counts in them and these sorts of things, and I need to be able to do, marginalization and renormalization and all that sort of stuff. Yeah, that you can just,
Okay.
Please don't go all the way to here is an implementation of LDA. But sure. Yeah. Emma.
I also have questions about the assignment.
Okay.
I'm going to start with problem 4. So we have to perform. Sorry?
Is that the linear regression one? I can't remember. Is that linear regression?
Yes, okay. It's the linear regression one. And it's asking to perform the Metropolis Hastings within Gibbs on the blocks W and T, and then pure Gibbs on both W and T. When I Googled blocks, it said that that's like W and T grouped together. So that would be like joint probability of W and T. Mm-hmm. Is that what it means?
Yep.
And then on both W and T, would that be probability of W, probability of T?
Yep.
Okay. Then, leading from that, to do the Gibbs sampling for just the pure Gibbs, we need the conditional distributions of,
Yep.
say, W based on everything else, which involves an absolutely disgusting integral. So is this so I've tried looking it up, and I know that the integral for Gaussian has a nice form. I just I feel like I'm looking at the wrong things, because
I think you're probably. My guess is my guess is, and we'll figure this out, and we can do this privately if you want to. We let people go unless people have the same concern. My guess is that you're probably looking slightly too low level, rather than looking higher level. So if you actually write out the densities and you write out the integrals and you write out that sort of stuff, you should, like, you're going to end up completing the square so many times that you want to die. Okay?
Yeah.
Right. So the point of this exercise is in fact to, number one, complete the square once if you've never completed the square before, but then figure out how to map the problem specification onto marginalization and conditioning in multivariate Gaussians. So, like, what's Bayes' rule in multivariate Gaussian? So, like, I keep putting this up there, but like I'm telling you, the answer is like immediately derivable from page 93 in PRML. PRML, you can get a PDF.
What book do you keep referring to?
Yeah, so this is, pattern recognition and machine learning. And if we weren't in COVID times, you would come to my office. I have 3 copies, and I would give you a copy of the book, right? And I would say, stop. Once you square, once you complete the squares one time, now you know how to do all of these derivations. They're horrible. They're nasty. They've got lots of matrix expressions in them. They're very difficult to get right, even. But if you think about what's going on in terms of like what conditional, so what's the joint distribution, what's the conditional distribution, what's the normalization constants, these sorts of things, you can cast this directly, almost always, and in this particular problem, in every instance, directly into, here's a prior that's Gaussian, here's a likelihood that's Gaussian, the posterior is going to be Gaussian, and it has this particular form. And you don't have to do any of the integration or the completing the squares. Okay. Because you just know it from this table.
Yeah. Then I have another question about problem 4.
Great.
And I asked it in Piazza, and Baron answered, and I think I just don't understand enough to understand his answer too.
Great.
Because, and I haven't had a chance to read his follow-up to Naomi's question, so maybe that answers, but I'm here now, so I might ask anyway. So the question gives us probability distributions that have a variable t, but then we are asked to show and derive the updates required for a variable t hat, which is a future prediction.
Mm-hmm.
And the slides in, like, your slides from, I think, lecture 3 had the linear regression graph with a t hat, but it also had an x hat, and then the probabilities listed on that slide had t hat and x hat mentioned in them in addition.
I see.
And so I'm not entirely sure how the ones that were given in the question relate to the t hat, because t hat doesn't appear anywhere in those, and so I don't know if I'm supposed to come up with that.
I wonder how you guys are. I wonder how you're all answering this. This is pretty impressive. Yeah. I think what has happened here, yeah. Yeah, I need to update the homework. So T hat is indeed meant to be. I don't know why it's on here. How did you answer, Bernd? I don't want to undermine you completely.
I'm really sorry for this one. Like, I was just focused on answering the LDA and the grass. So like for this one, you had solutions previously. And also I have to really apologize if I send you down the wrong path, Emma. Like I did not have a lot of time to
No. You
absorb
didn't
this
send
and
me down
think
the
about
wrong
this.
path at all.
Okay, yeah. So T hat is meant to be an out of sample prediction. Basically, that it is exactly what it's meant to be in the lecture notes. So so I mean, I can go back to the lecture notes, or we can just do it again here. Makes me sad. So yeah, that's totally my bad because I didn't put the T hat term in there. That's just completely silly. Yeah, so we've got W alpha Tn Xn. I guess this is n of these, and then there will be a T hat and an X hat. This is known. This is known. This is known. That's not known. That's a parameter. That's unknown. Is that right? That should be right.
So T hat, or sorry, X hat you said is known?
Yeah. And sigma squared. Yeah. And just to make sure we're 100% okay, when I say perform MH within Gibbs on the blocks W and T hat, I'm saying that there is one block which is W and one block which is T hat. And I only use, so I now that I've read this question and answered, that's different to what I said before, right? You could do either, it would be fine, but the point is not to actually make it unbelievably complicated. The point is to say, okay, write an MH operator just to show like that you know what the MH operator is within the Gibbs sampling context for this and for this.
Okay, and then for the probabilities that are given, we don't have like no hats appear in those. So do we have to determine?
So what I'm saying is that I should write that what I did not write down. I'll write down. I'll do it right after class or whatever. I did not write down the fact that T hat is governed in exactly the same way as Tn, right? So literally the T hat is. What I forgot is that there should be a T hat as well. I could have said Tn plus 1 and we would have been fine, basically.
Okay.
But there is a T hat which has exactly the same law as Tn. It's just
with X hat instead of Xn?
Yeah.
Okay. Thanks.
No, thank you. That's that is a use a new homework in a class that you haven't vetted from a year before, and this crap happens. So I apologize.
I just want
have
about
okay, go ahead.
Oh, sorry, it'll be quick. It's building on what was just said. So I just wanted to make sure, because in Metropolis Hastings, the lecture that we did on it, we didn't really talk about out of sample predictions. Like we sort of had like m random variables, right? Like x1 to xm. So in this way, it's kind of like if we take all of our t's, our t1 to tn, we end up having like n plus 1 random variables because our t hat is just considered as another random variable. Is that the way to look at it?
So if you're doing, let's just, just for the fun of it, let's let's look at this one just for a second, right? So what we need is P of T hat, okay, given everything else. Okay, but we know that's proportional to the joint, right? So we know that's proportional to the joint. So, you know, we can write down the whole thing, but let's just do product over n of P of Tn given in particular, really W and P of W given alpha, this whole thing, and then P of T hat n, T hat given W and X hat. Yeah? Okay, so when we do the Metropolis-Hastings ratio for computing this thing, right, the ratio so we'll do like P of T hat prime given over P of T hat given We'll do min 1, and this would be, sorry, I should erase that too. This will be the acceptance probably of T hat given T or whatever, I forget the notation that I used is, right? And we have our Q's in here, whatever the Q's are, doesn't matter. Let's assume that those cancel because we'll just use whatever symmetric proposal. You will note, if you look at what happens here when we write the Metropolis kernel for sampling from the conditional distribution of T hat given everything else, that the only terms that appear, literally the only terms that appear with T hat in them is that.
In the min expression, I can't see very well what was written. It's like P of, is that T hat
prime? That's T hat prime.
Mm-hmm.
That's like the new value that you're considering, and this is the old value.
Okay.
Right?
Yeah.
And if you write down that, remember these are the conditional distributions in the Gibbs case, but we know those are proportional to the joint. And in Metropolis-Hastings, we know that because of the proportionality, the normalization constants cancel, so we can just write this as the joint here. It's totally fine. Where the only thing that changes between the two expressions is the value of T hat and the value of T hat prime. And if you look at the joint distribution, the only place where T hat or T hat prime appears is over here. That's it.
So you get a ratio with just those terms.
You literally just get a ratio with those two terms.
Great. Cool. Makes sense.
Right.
So really for the question, we're just supposed to calculate the probability of T hat prime given everything else. Like that's what you want us to show.
At the end of the day, really, I mean, I've just given you the answer to like, you know, like what is, this is the answer to that question, right? It's like, okay, you know, what are the updates required? Well, the update is that you need to compute an acceptance ratio. Like basically for a Metropolis-Hastings algorithm, you need to tell me what the acceptance ratio is and what the proposal distributions are. So you're going to pick some Q's and you can say symmetric on whatever, and I need an acceptance ratio. Right. And what I want you to see on your own by struggling is that, you know, when you do Metropolis-Hastings within Gibbs, you're just sampling from the conditional distribution. And if you really actually look at that even further, you could say, actually, when I'm sampling from the conditional distribution, and this is where things get a little bit funny, like if you went one step further, you would say, actually, if I'm conditioning on the value of W, I'm conditioning on the value of X hat, and I'm conditioning on the value of sigma squared, which I erased, sorry, right? Then the conditional distribution of T hat, given all those things, is exactly what you read off the graphical model. So in fact, you don't have to do anything. You literally just sample from this because it's normal. So you know, you could like you should be like, hey, idiot, you know, even though you can do this Metropolis Hastings thing, really what you've just written down is how to Metropolis Hastings sample from a Gaussian. So why don't you just sample from the darn Gaussian and be done with it, right? So that one you can just sample from the Gaussian. This one, yeah, you have to be a little bit more careful because you have a posterior distribution, and when you write the ratio, you just write the ratio, you'll see that when you Gibbs sample on that, you actually have to take into account t hat. And this is where I get confused because t hat, when you're Gibbs sampling, looks exactly like one of these. It has, you might as well just pull it in, it has exactly the same structure. So when you write it down, you can sort of forget about this and you can say, okay, what is the posterior distribution of W given some number of observations? It's either going to be given n observations that are also Gaussian distributed, or it's going to be given n-1 observations. And those are going to be Gaussian distributed as well in the exact same way. n+1, excuse me.
Yeah.
So the posterior distribution of W, so like, you know, the posterior distribution of W given everything is proportional to the product of, you know, P of Tn given Xn W over all n, or n+1 times P of W given alpha. This is normal. And if you think high level a little bit, you can also write down this as vector normal. I guess, you know, you can you know, like you have t, the full all t's, you know, whatever, you know, given a column vector. So let's go with you know, x1 transpose x2 transpose the xn transpose W will be normal, this x vector times W, and covariance matrix, which is sigma squared on the diagonal. So now you have a normal setup, and that you can run Bayes' rule on. Because you have multivariate normal, you have multivariate normal posterior, then you have both the posterior that you can sample for Gibbs sampling, and you have, when you look at the Metropolis Hastings ratio, you have, you will see all the terms cancel in the same kind of way.
Thank you.
Why did you expand it to a covariance matrix there? Doesn't the transpose multiplication like result in a single value for the mean, or?
No, so there's like there's a vector of target. So T here, I should have written T1 to T2 to Tn, right? So you have the design matrix, which is X, which is all of the X vectors, which are assumed column vectors. You transpose them all, you get X is the big vector, is a big matrix. You multiply W into that. That gives you the mean for all of the targets, right? Yep. So you have an N vector, and by assumption, because of the IID assumption, those are all identically distributed with variance sigma squared, which means that multivariate normal is a diagonal with sigma squared on the diagonal entries.
Yeah, sorry, I wasn't paying attention that T is also like.
Yeah, I sort of.
My bad on that.
Just to make sure. So when Emma was asking about for this pure Gibbs portion, so she said like you need to do some like integral. So do we also need to compute the normalization constant just for the kicks, or like
You must. So to do pure Gibbs, you must have the distribution in closed form. You must be able to sample from the exact conditional distribution, unless you're going to do Metropolis within Gibbs. You have to actually compute the normalization constant. But computing the normalization constant with the Gaussian integrals is like impossible, right? It's totally impossible. But the hint from the earlier questions is to say, okay, actually think higher level, right? Think like, I hinted at least 100 times, and I'm going to do it again, just to, page 93 PRML, right? Or whatever, Sam Roweiss's Gaussian notebook, like Gaussian cheat sheet, whatever. You can get Bayes' rule for multivariate Gaussians, which means that you can actually derive, effectively what it means is that you know the normalization. This is saying, like, look, let me just map it for you right now. Let's see. Are you ready? Okay. Yeah. So you have P of X, that's P of W. Then you have P of Y given X, that's P of T given X and whatever, right? So there's some linear factors here. Those are the linear factors from linear regression. Basically, there's a prior and a likelihood, and those that have these forms. They have some parameters, right? What Bayes' rule for Gaussian says is that you can get, you can't really see, you can get the posterior distribution of X given Y, which would be, in our case, the posterior distribution of the weights, W, given the targets and the inputs. And that comes in this particular form, which is like, you just look it up. Okay. Somebody did these integrals for you. If you have to do these integrals, my God, you will so part of being a graduate student is trying to figure out the easiest path through everything when you're confronted with some horrible, nasty, horrible problem, right? And you have to imagine also that I wouldn't actually want to throw everyone out of the course by making something totally impossible, which means, in fact, with this and the setup that I just gave you of normal, like literally it is look up and plug into equation 2.115, right? Sorry, 2.116. Don't let me get you. Don't let me let you go wrong. 2.116, and really what I want is for you to understand, like, there is a Bayes rule for Gaussians. Gaussians are closed. They're conjugate family. They're conjugate to themselves. They're closed under normalization, conditioning, marginalization, so on and so forth. And you need to be able to say, okay, I've got a Gaussian now, bang. I know what the posterior distribution is. I know how to condition and marginalize, right? Okay. And just be comfortable with that. And the best of you will have done the complete the squares exercise one time, which means basically you will complete the square and then recognize that there's a Gaussian integral because you see that the form is a quadratic form on the top, and that means that you know how to write down the normalization constant, only because somebody else has actually done the integral and shown that the Gaussian distribution is a Gaussian distribution. The same way that like the Dirichlet, I mean, who the hell is going to derive the normalization constant for a Dirichlet distribution? My God, that's a terrible integral, right? Somebody did it, but you have to be able to operate. We're going to be operating at a higher level using these tools and this understanding. I've done it. We've all done it. The good machine learning people, we all have to do it at some point, right? And then you just have to take it on faith, believe it, and use the results, right? So the results that we want to use here and make you aware of are these Bayes rule for Gaussians, and just be very, very fluent with them, because then people who, for instance, for some people in my group who have done Kalman filtering and these sorts of things and not known what the heck they are doing, they should be able to figure out how to do Kalman filtering or forward-backward in linear Gaussian dynamical systems using these Bayes rules straightforwardly. In fact, the alpha message that I was showing you in the lecture today for forward filtering, backward sampling, that alpha message can be computed in closed form for linear dynamical systems using Bayes rule for Gaussians, right? And the exact same thing can be done for HMMs with linear Gaussian backbones, right? So little stuff to, I've thrown a lot at you, but it'll come.
I have another question.
Go for it. You got me. Go on. Yeah.
So my understanding of Gibbs sampling is that the result you get in the end is a way to characterize the joint probability distribution of all variables. It is
the whatever distribution you're sampling from. It can be joint or posterior or conditional or whatever. You're sampling from some distribution, and it has some support, and you're going to get samples from the support of that distribution. Correct. Yeah.
Okay, so that's where my understanding fails.
That understanding should be reinforced by the fact that if you were able to derive the fact or understand the derivation of the fact that that Gibbs sampling is an instance of it basically satisfies detailed balance. So it is an instance of a Metropolis Hastings algorithm that never has to reject. So Gibbs sampling is just Metropolis Hastings that doesn't have to reject, which means that it has all the same characteristics as Metropolis Hastings. It's like all the theory that we went through last time applies to Gibbs sampling. So you can.
I think my confusion is from a different spot.
Cool.
Because I know you like the basic step of Gibbs sampling is like I sample probability of like I sample like x1 based on x1 conditioned and everything else. Then I go to x like your slides where you said we're at like x2 and I sample x2 given probability of x2 given everything else, so on. And so then the result you end up with is like a set of samples that approximate your underlying distribution.
Correct.
To me, I don't understand how the underlying distribution is something other than the joint distribution of all of the variables.
So when we're doing, okay, so if two situations, right? Okay, so we have some distribution here. Okay, one could run a Gibbs sampler for any of these, for this joint distribution, correct?
What do you mean by that?
I mean, you sample A condition on the values of B and C, sample B condition on the values of A and C, sample C, so on and so forth, right? So you could sample from the joint distribution using Gibbs sampling.
Yes.
In fact, we ask you to do that, right, for the wetgrass example, right? Cool, okay. Fine. Great. Now let's say that we're doing posterior inference.
So then like C is fixed because we see C. And so like I guess I understand that. So then when you fix one of the variables, it becomes a okay. Oh, okay. All right. And so then if you what's my next question? So then what we're doing in problem 4 would be because sigma squared and alpha are fixed parameters, then it would be like t x. Oh no, but we also know t and x.
We don't know t. We know t and x for all n. We don't know
n,
t hat.
but not the hats. Yeah.
We know x hat. We don't know t hat. Yeah.
Okay. So then, what we would do we know w? We don't know w.
Nope. W is the principal variable of interest.
So then, inherently, what we get from the Gibbs sampling here would be probability of w and t hat conditioned on everything else. All right. I think I'm understanding it better.
Yeah. Thanks. Yeah. And the miracle will happen if and when we are able as a team, all of us, to not only so the first bit is like we do a bunch of crazy applications to say what we can do. Then we get these algorithms and we write them in a general purpose way. And the miracle of all miracles at the end of the day will be if you can then go back and actually frame problems using like what this posterior distribution means. So like in this linear regression case, think about what it means. Again, I want you to be thinking about that while you're doing it. The posterior distribution over W is I've got my X's, I've got my T's, and the posterior distribution over W is a distribution over these lines, right? And the posterior distribution over T hat for a particular X hat, right, is going to be the distribution over the prediction at that whatever out of sample value is, right? And a crap ton of stuff can be expressed in this probabilistic framework. That's just conditional density estimation and out of sample density estimation. So once we generalize away from linear forms and once we generalize away from, Gaussian likelihoods, basically all of supervised learning lives in this. Bayesian neural nets live in this framework exactly. So like wrapping your head around what the posterior means is super important. Wrapping your head around how to get it algorithmically is super important. And then hopefully over the course of the term, that will leak in and you'll be able to think about how to take a supervised learning application and like whatever the supervised learning application, classification application is, whatever, and smack it down as a program or an inference objective like this, and then just solve it using our automated tools. But that's what I somehow have to automatically make happen in this course while actually talking about programming languages and inference and that sort of thing. So the thing I actually care about you learning is something that's almost liberal arts like. It's like how to think about framing problems in this way so that you know what the posterior distribution is, so that you know how to, and once you know how to get it, then it's more about framing the problem in this way, and then just letting inference do its magic. But you kind of have to wrap your head around what the posterior is, and then there's a lot of stuff to sort of internalize. It usually takes most people like 2 to 3 months to sort of kind of look at things in the inference kind of way and get used to thinking in terms of posterior inference and what conditioning means and what the posterior distribution is and what it's a shift. Some people like it and some people don't.
Thanks.
Anything else? Given that everybody was here, I might not actually make the switch to T-hat tonight. I'm hungry. I want to go home and eat. So I might postpone that till tomorrow. So everybody knows what's going on with that problem. Thank you for identifying the problem. I saw it on Piazza and made Baron try to deal with it. Okay. Thank you all very much. It was lovely.
Thank you.
Good evening.
Thank you.
Cheers.